263. Let's go. A uniform ball of radius r rolls without slipping down from top of a sphere of radius r. Find the what angular velocity of the ball. Okay, at the moment it breaks off the sphere. Okay, cool. At the moment it breaks off the sphere. That's kind of a hard question because you have to do a lot of stuff for this thing. So it uh, rolls without slipping down from the top of the sphere of radius r. And that sphere is like stationary or what? I think stationary. Fine. You got this sphere, you got a small ball, right? Yeah, at some theta value. So let's just say this thing is theta, right? So at some theta value, it's going to break off. What is that value? And when does it actually break off? It will break off when the normal force is not sufficient or something like that, right? Yeah. So we'll figure out that condition. First of all, we just want to do it for general theta values. Right. So it's of what? Small. Okay, a uniform ball of radius small r. This is capital R, right? This thing is small r. Right. Finding the velocity of the ball at the moment it breaks with the speed. The initial velocity of the ball is negligible. Right. So at this point it was at zero velocity, then it goes down like that. And since it's just rolling, there's no friction. I mean, okay, the friction doesn't do any work, which means you just do energy conservation and get the thing done, right? Okay, so this is r and so like capital R plus small r, I would say. This thing is going to be capital R plus small r times 1 minus cosine theta. Right, cool. So that's awesome. And then you also want the energy at that point. So it's moving with some kind of velocity. It also has a kind of angular velocity. Yeah. And at this tangent, right? Okay, this tangent, uh, that point, right? This point is actually stationary with this tangent as well, not just with the sphere, but the tangent as well, of course, because yeah, um, right. I mean, this point must be stationary. That's the whole thing. So yeah, like v equal to omega r for this thing, right? So the velocity v, this thing is zero. You've got omega. It's hard to actually explain this, but that's the thing. All right, that's the thing. So what can you say? mgh, right? mg, then you got r plus r, so let's cosine theta, half I omega square. So it's a sphere, right? It's a ball, so solid ball, I think, right? So about this point, what's the inertia? It's just equal to, and of course like half I. So inertia is 7 upon 5. Is that right? It must be right. Of the mass and then r squared. Okay, and this times omega square, or you can just say v square upon r square. So this thing is v right there. And what do you want? Angular velocity. So actually just deal everything. Yeah, just use omega everywhere, right? Okay. Guess that should make sense. So there you go. You got the equation, first equation. Cancel some stuff out. You got r squared and all that stuff. Okay, that's 7 upon 10. So 10 upon 7 times r plus r times 1 minus cosine theta. That is equal to, you got r squared, I think, right? R squared omega squared. Or you just say this is equal to 7 r squared omega squared. That's one equation that you have. So given the theta, you can figure out omega all the time. It's equal to 7 r squared omega squared. Perfect. So you know one equation. That's from the energy conservation. All right. Angular momentum conservation, well, you can't because friction is varying its direction. So there's no single point where you can do the thing. Okay, you can't. Well, whatever. Force analysis. So at this particular point, this guy's center of mass is moving like, okay, this has acceleration in this direction only. Actually, no, not only. It also has a tangential acceleration. So it's dv upon dt and all that stuff, right? This is just equal to 7v squared. You could get the dv upon dt thing easily using just that, right? Well, no, you will, that's kind of hard. Okay, so v as a function of theta is given. Yeah, well, whatever. Maybe we won't even need that. Who knows? So you got normal force. You got some friction force. We don't care about the friction force. We only care about normal force. Normal force, right, is over here. And then it's like gravity as well. So you got mg in that direction. This is theta as well. So mg cosine theta is in this direction. So like mg cosine theta minus normal force, that is m omega square r. So no, I should not say it like that. It should really just be mv squared upon r. Because we already used omega for a different omega. So you can't use it for v upon capital R plus small r anymore, right? So it's mv squared upon capital R plus small r. That makes sense? So you got the thing, you got normal force. Yeah, and when does it break off? It will break off whenever n is, yeah, right, exactly. N becomes, and friction, there's no coefficient given, so just assume it's very rough, right? And then friction is always sufficient. Okay, so it is n equal to 0, that's our critical condition, that's when it will break off, because n won't be necessary for it to move. So yeah, it will fall off from the circular path. And there you go, that's our condition. So isn't this like just 7v squared? Yeah, just use 7v squared and not r squared. You can do the omega stuff later on. That's awesome. So you got this thing and you also got that thing. And now what do you want? Oh, you could just, cancel the theta out, right? Of course. So yeah, okay, 7v squared upon 10 times of r plus r, that's equal to 1 minus cosine theta. And let m cancels actually. V squared upon g times of, something's weird about this thing. Oh, there should be a g over here as well, because mgh. So that g. Uh, yeah, then you just put that g over there, like 10g or whatever that is. Okay, 10g. And this is what? You got g down, you got r plus r once again. That's just cosine theta. Cool. And then just add. So 1 is equal to v squared upon g times of r plus r, and then you got 7 upon 10 plus 1, right? Which is 17 upon 10. So you got your v square. V square is 10g r plus r upon 17. Is that right? Yeah. And then, okay, v is just square root of that thing. So this thing upon small r is what is our omega, right? That's the angular velocity. Where did that question go? Right. So, omega is just this thing upon r. So, square root of 10g r plus r upon 17 r squared. Cool. That's our answer. That's kind of nice. Okay, next question. All right, 264. 64 is a uniform solid sphere of radius r equal to something rolls over a horizontal plane passing into an inclined plane forming an angle alpha 30 degree with the horizontal. Okay, like this. Find the maximum value of the velocity v naught, which still permits the cylinder to roll into the inclined plane section without a jump. Without a jump. Okay. The sliding is assumed to be absent. Huh. Without jump. So, like, okay, at that particular point, right, what's happening is, so just before it actually does whatever it does, it's at this point, like this guy's center is like this. And in order for it to start rolling on this incline, what must happen is that this guy's center should move like this. So throughout that, throughout that, it's on a single point. It's just doing circular motion on this single point. That makes sense? And it's also not, yeah, okay, there's no slipping, right? Sliding is going to be absent at this point as well, and it is not jumping, right? uh yeah, if the, wow, this is weird. What does it mean that when it jumps? What it means, of course, is that its surface doesn't touch it instantaneously. But in terms of kinetics, what does it actually mean? I don't know, right? Ah. Maybe this guy falls off, so it has to cover an angle of alpha before it goes on this inclined plane. So maybe this guy just falls off before alpha, right? So yeah, for like, okay, what if its velocity is so big that it actually cannot do this? Right. I think that's what's happening, isn't it? Now there's gravity. There's gravity that's providing centrifugal force, and there's normal opposing a bit of that. Right. So what if, you know, the gravity is not sufficient? Then it's gonna fall off because it cannot be in that circle anymore. It's going to go like this or maybe something like that, right? So for some while it will go like that and then it goes like this. So this point is where it falls off. Does that make sense? Okay. Right. Let's do the thing in that case. So it's moving with V naught, and then initially it was rolling or not. Rolls over a horizontal plane. At this point as well, just before the thing, it was also moving with V naught. Okay, so its angular momentum is fixed. No, actually, it's that the gravity is going to make it. Right, it's not fixed. Ah, okay. Let's not think about the whole sphere. Just think about these 2 points. This point where it's rolling over, and the center of mass. So initially just V naught in that direction, right? And then after a while, it's V in this direction. So suppose it actually goes by angle. Let's enlarge this. So let's not think about alpha equal to 30 degree, but some really big alpha for our convenience, right? So this is the thing, like at some point. So it's making angle theta. Then r times 1 cosine theta is what? Yeah, you can use that to get your V because rolling, right? So r times 1 minus cosine theta, g times of that is equal to half delta V square, half V square minus, so V is actually going to be bigger, right? Okay, so you know V square upon R, that is equal to, this is weird. What about the friction coefficient? Is that given? Nothing's given about that. Okay, so then just assume friction to be infinity. So V square upon R, that's equal to V naught squared upon R plus uh, 2G times 1 minus cosine theta, right? Okay. V square upon R is the centripetal force. It also has this tangential force. We don't care about that, do we? No. This thing will just be, what is this really? It's mg and what? Okay, it's theta, mg cosine theta minus normal force, right? That's equal to this thing, 2g times minus cosine theta. Oh, actually, no, it's acceleration. It's not, right? So just say n upon m in that case. So n upon m is equal to what? It is g times cosine theta minus 2 plus 2 cosine theta, right? So that's just equal to g times of cosine theta minus 2. Wait, that's actually negative. Why does that happen? Something's weird about this. Uh, yeah, how did that happen? Oh, it's 3 cosine theta minus, right? Sorry about that. So it's 3c minus 2. So, right, initially theta is 0, so it's 3 minus 2, just g, which makes sense. Okay, so n upon m is this thing. This must always be positive or equal to 0 throughout. It cannot be negative. In that case, throughout the motion, that rolling motion, your cosine theta must be bigger than or equal to 2/3. This is not nice. Wait, something messed up, right? Oh, there's this thing. How did I miss that? Yeah, it's supposed to be this plus v naught squared upon r. Perfect. That's gonna be the thing. So n upon m is equal to this minus v naught squared upon r. So yeah, this actually is like, this thing is bigger than or equal to 0. Okay, that's how it's supposed to be. So throughout the motion, and as your theta increases, this thing actually decreases because theta was, cosine was maximum at 0, right? It's going to change till alpha, of course, because yeah. So what does that mean? Maximum value at, no, the minimum value at alpha, right? So even at that point, just got g 3 cosine alpha minus 2 bigger than or equal to v naught, v naught square upon, yeah, actually v naught square upon r. Yes. So you got the minimum value in that case. Perfect. And after that, we don't care about this thing anymore. Normal could be 0. Yeah, because it's not rolling in that kind of way. Okay. So v naught is less than or equal to square root of rg times 3 cosine alpha minus 2, and that's our general form. And in this particular case, what is the thing? Alpha is what, 30 degree? Oh, what happened? Okay, this is right. So alpha is what, 30 degree, and that's going to be Rg 3 upon 2 minus 2. That doesn't make any sense. Doesn't it? Oh, if cosine, oh, sorry, it's square root 3 upon 2. So it's like 3 square root 3 minus 4 upon 2, and 3 square root 3. Like square root of, okay, wait, 3 square root 3 is bigger than 4, right? Because this is the square root of 27, and that's the square root of 16. So, yes, there we go. And that's in the square root once again. Why? Uh, if it was 2 or something, it would have worked. It's not going to work like this. Yeah, right, whatever. And then you got RG. And what's G, by the way? Just assume it's 10 or something. What is R? R is 15 centimeter, right? So that is 0.15. Yeah, so like 5 times 0.15 is 0.15 times all of this, 3 square root 3 minus 4, and the square root of that thing. This is what V naught max is. Square root of, what is this thing? 0.75, which is 3 upon 4, of course. So 3/4, and then 3 square root 3 minus 4. Why is this taking forever? Okay, whatever this value is, I won't do it. Yeah, just leave it like that. Or if you really want, write it a bit differently. You can write this thing as 9 square root 3 upon 4 minus 3. That's it. That's as far as I can go. There we go. This is the thing. Next question. 265. Okay. A small body A is fixed to the inside of a thin rigid hoop of radius r and mass equal to that of body A. Any figure given? No, figure 1.68. Okay. Which is this thing. So a small body A is fixed to the inside of a thin rigid hoop, radius r, mass equal to that of body A. The hoop rolls without slipping over a horizontal plane. Okay. At the moments when the body A gets into the lower position, center of hoop moves with a velocity v naught. At what range of v naught will the hoop move without without bouncing? Why the okay? So it should not bounce. Interesting. When will it bounce? If it doesn't bounce, then of course normal force, it can, yeah, it is in contact with this surface. In that case, there is a normal force, or maybe there's no normal force, but it's still in the contact. So n is bigger than or equal to 0 for it to be still in contact. And if it's gonna bounce, so you could think of it as n less than, I know it doesn't make any sense, but right, so at the point n equal to 0, it could bounce, right? That's our critical condition. Okay, no big deal. We can do this thing. So yeah, let's do this. It's moving it not that central point, right? Interesting. And that point is stationary. You just find the inertia at that particular point. And friction is not doing any work, I think, till that point. So okay. Hey, when is this tendency to bounce the highest? Whenever the normal force will be the lowest, right? And when does that happen? When is your normal force the lowest? Something's weird about this thing. Why is normal force changing in the first place? Because of this mass, it's going up. That causes the center of mass of this guy to go up, right? There's gravity, of course, but that's constant. That's why normal is changing. Sure. And this rate of going up is also going to change. That's why normal is changing. Okay. Wow, this is very weird. So what is the normal force at any given moment? So x is at like some angle theta. This angle is theta over here. This is moving with omega with respect to this guy, of course. This is stationary, we know that. Yeah, this complete guy center of mass is not really changing, but this guy's mass is changing. So yeah, just the mass of this a boy times acceleration of that a boy. So what is that acceleration? Oh no, it's hard to do that because This V naught thing is also changing, so you will need that. Ooh, that's not good. Okay, so you got V naught, okay, V, right, and omega. Cool. Uh, with respect to this guy, but then this is also moving at omega, so you could just say V equal to omega R actually. So, right, alpha and stuff. Cool. So with respect to this guy, it has alpha R acceleration in this direction, and you know, omega square R in this direction. Sure. But actually this has alpha R in that direction as well. So you have to do all that, and after that you will get the final vertical force. Or this is painful. What? This is the complete acceleration of A. Okay. There's friction that takes care of the vertical components. Sorry, of the horizontal components. For vertical components, we need gravity and normal. So you got this. Wow, this is just so bad. Uh, okay, this angle was theta. This angle will also be theta. So this is angle theta over there. Omega square r cosine theta, and that's 90 minus theta. So like alpha r sine theta. That is the thing. Okay, that times this guy's mass, small m. Okay, that is our final force. Now just equal to what? Normal force is going up, right? Well, yeah, it's going up. Minus mg. So the normal force is equal to this. M times of all of this. What is this? So g plus omega square r cosine. And moreover g, okay, like omega and alpha change. So it's gonna take forever. And then plus alpha r sine theta. And now we need to figure out what omega is depending on what theta is. Why? Okay, so what's the velocity of this guy, huh? I mean, it's omega r in that direction, and this guy is moving with omega r in that direction. So why is this the thing? That's no way of doing it. There's definitely no way of doing it. No. So omega r in that direction, omega r in that direction. But this whole thing is a rigid body, and then you got this point with respect to, yeah, this point is stationary, right? So with respect to each point, this must be going with omega r. Wait, what? I mean, it depends on what the, why did that happen? Oh yeah, okay, this point, okay, this changes, right? Okay, so you need the inertia in that case. So it's still just half I omega square. That's our energy, kinetic energy. And that's equal to, well, what is this? Uh, Staying forever. Okay, the change in that energy. Ah, what's our reference point? This must be our reference point, I think, right? So yeah, omega square minus omega naught, or like the difference. So it's this thing, omega naught square minus omega square. Okay, and that's equal to the change in the potential energy of the gravity, of course. So okay, and that's only because of this guy. So it's small m g, and then the change in height of this thing, which is this angle is theta, it's cosine theta, like that. So r times of 1 minus cosine theta, of course. Now we need the inertia at every single theta value. This is taking forever. Is there really no other way of solving this without having to do all of this? Come on, think about it. You could just, do a bit of cheating and just think about the final critical conditions, n equal to 0 and whatever, right? And then when does that happen? Something like that. And so as theta increases, your cosine theta value that decreases. The sine theta value actually increases till this point, but then after that it starts to decrease as well. So the minimum value is of course at this point, because that's when cosine theta is negative and sine theta is also just 0. So at that point your normal is the minimum. You could do that thing. I just want to do it the correct way, but it's taking forever. And also, like, okay, when it goes over there, omega is actually the minimum. Oh, that's not nice. Yeah, you have to figure out omega for this thing. Right. Okay, so what's the inertia? Uh, Actually, it's not supposed to be this thing. It's supposed to be, the initial inertia is like, okay, I naught omega naught squared minus I omega squared, like this thing, right? So for theta value, you know what this thing is, I guess. Right? It's just r sine theta, 2r sine theta upon 2, so the square of it. It's gonna take forever like this. There's no way I can do it on time. Well, this is interesting. I think I'm going to do it later in that case, because there must be some alternative method for this thing, because I can't be doing this the way I am right now. So weird. 266. Okay, 266 is determine the kinetic energy of the track of a tractor crawler belt of mass m if the tractor moves with velocity v. So 1.69. So moves with velocity v. Hey, this is actually a nice question that I've seen like everywhere basically. Actually. So this thing, right? Or me just not do that actually. Uh, Fine. I mean, you could do it. No big deal. You could do it like that. The center of mass frame and all that stuff, right? Sure. The energy of the center of mass and energy as seen by center of mass, add both up. You can do that because of the v square stuff. Right. That cancels it. Sure, it's gonna work out. No big deal. So center of mass is somewhere on this line. It's gonna move with v. So yeah, you got half mv squared, and then plus as seen by center of mass. What's the energy as seen by center of mass? Like this point is moving with velocity v. This is moving with velocity v in that direction. Sure. So all the points are moving with speed v. Yeah, that's what matters. So half mv squared once again, and that's why mv squared is the final energy. Yeah, that's a good thing, but I mean, is there no better way of doing this? So you could, okay, we run into this kind of approximation where you say these wheels are really small or something like that. Or you could do it by breaking into parts. Both will give this result in the end. Well, whatever. I think this is the best way to do it because it's the most tidy. 267. Uniform sphere of mass and radius r rolls without sliding over the horizontal plane, rotating about, so this thing, about horizontal axle OA. In the process, the center of the sphere moves with velocity v along a circle of radius r. So this is sphere and this axle. Okay, it's rotating like that. Okay, cool. Sphere moves with velocity v along a circle of radius r. Fine. Fine. Find the kinetic energy of the sphere. Hey, it's not that hard actually. So it's just the energy of the center of mass plus energy as seen by center of mass, right? So as seen by center of mass, what is really happening in the same reference frame as the ground frame, right? I mean, okay, the same, yeah, the same coordinate x or something like that. It's not a rotating reference frame. That's what I'm getting at. It's not a rotating reference frame. You have to be sure that's not happening. Okay, so then this center of mass, it's like over here, whatever. It's having a velocity in that direction, right? And yeah, okay, this point is moving like that, okay, with some higher velocity. With respect to center of mass, what's really happening is that this point is moving with omega. Yeah, so this point A with respect to the center of mass C is moving with omega. So and this point as well, call this B or whatever, right? But there's an extra thing going on, that this thing is going with some kind of velocity as well. So this is like, yeah, this circle is moving with a different velocity. Okay, this is hard to explain, but I have already told you how to do these kind of things. Where you got an axis which is rotating about another axis, so you just superpose the angular velocities. So, yeah, right. This axis is rotating about the z-axis. The angular velocity is omega, right? Or okay, what they gave us? They gave us the velocity v naught, right? Wait, no, that's not 1 point. Something's weird about this thing. Where did the question go? 1.7? Oh, this thing. Right, so it means velocity v, then you can actually figure out what this omega is going to be. Just going to be v upon capital R, right? And what about this distance? Small r, fine. So, right, it has omega in this direction, which is v upon r, so capital R. And also, with this, in this rotating reference frame, this thing is actually moving like that. So it has, and this point is stationary, right? In that rotating reference frame. It's kind of hard to explain what's going on. Right. Right. This vertical stuff, it doesn't. So it's going to be r cross v. So sorry, r cross omega. This vertical omega vector doesn't matter for this thing because r is completely in vertical direction. So that cross product is going to cancel out in any case. So we just have to look for this omega vector, right, to get this guy's velocity. And then it's moving at velocity v. If that omega vector is like omega, omega is that thing, then just got v minus omega times this distance, which is like small r, that is equal to 0 because this is stationary in the ground plane. That makes sense? I know it won't because, okay. Look, you should really watch those videos of mine that actually explain what I'm doing. I can't explain while solving this question. Whatever. So you got v equal to omega r as expected, right? And in this case, omega will just be v upon r. So it is v upon r in this direction and also v upon r in this direction. Like this is the r hat direction, this is our k hat direction. That makes sense? So the net omega is actually somewhere in this direction. Sure. Okay. And now what do you want? You want the kinetic energy of this whole thing. So you can just think about like summation of mi, or you can just, yeah, let's not think about with respect to this point. Actually, let's think about with respect to this point. Why not? Right? Of course. So you can just do half mv squared to get the kinetic energy of the center of mass, and then you want the kinetic energy as seen as center of mass, which for that we just do half, sorry, just do summation of half mi, and then each guy will have a v, but v is actually just omega vector, the net omega vector, which is the sum of these two vectors, cross r vector square of that, right? Yeah, ri vector or whatever. So that was the thing. Sure, that's the energy. So it's like summation of half. It's taking forever, isn't it? So you want the square of this guy, you just take a dot product or something like that. Yeah, that's one way to think about it. So like summation of mi times ri, like that thing is 0. Cool. But this is a different animal. Your actual omega is in this direction. It's not that bad, is it? No, it's not. All you gotta do is um, just think about the r vector component that is perpendicular to omega vector. So you could just say ri perpendicular, and then this cross product will have that sine alpha factor 1. So you can just dissolve this cross product and write it like this thing. And then it's going to be omega squared ri perpendicular squared, right? And yeah, this is the sphere. Omega vector is pointing in that direction, right? Of course. And it's still along a diameter. So you can use half I omega squared for this case. Why not? So she's got half. The inertia is 2/5 mr squared. And then this omega vector, that gets squared, of course. Yeah, I mean, this magnitude squared, which is actually the same thing as this thing squared plus that thing squared. So you got v squared upon r squared plus v squared upon capital R squared. There you go. That's our formula. Just add up everything. So yeah, it's 1/5 over there. It is half mv squared plus 1/5 mv squared plus 1/5 of this weird stuff, mr squared upon r squared times v squared. There you go. That's your energy. So 5 plus 2 is like 7 upon 10 mv squared plus, you know what, should take mv squared common, because mv squared, you got 7 upon 10 and then plus this guy, r squared upon 5 r squared. Cool, that's our energy. Next question. This is what, 267? Okay. 268. Demonstrate that in the reference frame, rotating with constant angular velocity omega about a stationary axis, a body. What? Sorry. Oh, okay, okay, like that thing. Fine. Yeah, a body of mass experiences the centrifugal force of inertia. F is equal to, right? Okay. Yeah. Okay. Cool. And the Coriolis force F is equal to 2, blah, 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 whatever. Yeah. I mean, I've already done that. What's the big deal about it? Okay. Where V is the velocity. I already made videos on this thing. You know, pseudo forces and rotating reference frames. I've made videos on that. Go watch them. You'll understand what this is. Yeah, right. Where omega c is the velocity of body center of inertia and the rotating reference frame. Wait, you want this like for any body? Okay, that's a different thing. Oh, so you are centrifugal force of inertia. This is the thing. With a constant velocity omega about a stationary axis. Oh, a body of mass m exposes this thing. So this is a this is actually not a point mass. It's a body that is like a sphere or something like that, right? That's complicated. But this body could be any abstract stuff. So you gotta do it using discrete point masses, some of those things, right? Interesting. And what is this thing? Oh, this is like the cross product, isn't it? Of course. So that's the way Coriolis force is actually done. So just assume that these things work for a single point mass. That is, you can just say, right? The force on a single point mass, right? The centrifugal force, that's like m omega square times ri vector, right? Cool. I know it's more complicated than that, but yeah, right. I know it's more complicated than that, but think about it. It is supposed to be like this, right? Okay, no, I know it's not like that. It's actually like this thing, m omega vector cross all of that stuff, right? That's the way centrifugal force is actually done in 3D vectors. Interesting. Just okay, get rid of the z component of r and only think about the xy component. Does that make any sense? Because okay, omega vector is along the z component, get rid of that vector, right? And then you can just write it like that. So you thing omega vector cross omega vector cross. Okay, it's not supposed to be this thing. What was the thing? Omega vector cross r vector, that's a v vector, and then you want, I think, this cross. It's getting complicated. Yeah, I think it was like this thing. So r vector cross omega vector, right? So in the cross product, the z component won't survive anyway. So just think about r x y components only, and then you can do the thing. So use the triple product identity, and then you got omega square r x y minus omega dot. Yeah, that's gonna be 0. So that works out. Just gotta think about the xy component. So ri, but in just xy, right? And then sum this thing up, right? Yeah. Well, that's like omega square, and then you got summation of mi ri. Even in the xy components, this thing would actually just become the total mass, and that times the radius vector of the center of mass in the xy plane only, actually, right? What about the z component? We don't care about that. Yeah, we don't care about that. This is actually what it should be. It's not relative to rotation axis. Oh, okay, they did give us this thing relative to the rotation axis. Of course, not relative to a point. It's not relative to an origin, right? Like this thing. Okay, so yeah, A done, A done. What about B? So the Coriolis force is actually given by this thing 2m v vector cross omega vector, omega naught I should say. So the omega naught that represents the angular velocity vector of the rotating reference frame as seen by the ground frame or space frame or whatever. Right, and you want the total coherence force for a complete body. It's given by this thing. Okay, that's nice. So just gotta sum this up. Well, it's not that hard actually, because you can write this complete thing as a single vector. I don't know, call it what? Momentum vector? It is just that, momentum vector. So just sum this up. Net momentum. Easy as that. So it's like two, sum of this thing is going to be 2 total mass, velocity of center of mass, and then you got this thing. So yeah, exactly. This actually works out. There we go. So B is correct. I mean, it is, of course. That's why they're telling us to prove it. So that's done. Okay. Next what? 269. A midpoint of thin uniform rod AB of mass m and length L is rigidly fixed to the rotation axis OO dash as shown. Figure 1.71. Okay. Alright, and this is like that. The rod is set into rotation with a constant angular velocity omega. Find the resultant motion of the centrifugal forces of inertia. Resultant moment of the centrifugal forces of inertia related to the point C in the reference frame fixed to axis OO dash and to the rod. Oh, so as long as these bodies don't move, you don't need to think about the Coriolis force at all. Just need to think about the those things. So it's like it's because of symmetry that this is pointing in that way, but then it's the same mass pointing. Yeah, it's gonna cancel out. Or you can just use this formula. So on this comes, oh no, you actually want the torque, right? And about what? Uh, Related to the resultant moment of centrifugal. That's like r vector plus f vector, but in the reference frame fixed to axis OO dash and to the rod. Oh, okay, I understand. In the rotating reference frame, what is the torque? So basically, it's just zero. It's just zero because, like, yeah, symmetry. Look, the thing is, you got a dm mass over here and over here. So you got the force in that direction, and in this direction it should be df. But these just cancel. Okay, actually no. Oh, I think I messed up. Oh no, there's a problem. There's a problem. Even though these forces cancel out, the torque is not canceling out somehow. That's unexpected. Right, because, oh god, that's wrong. Torque is not zero. Ooh, this is not going nice today. Fine, you gotta do the thing in that case. So, integration of dm, I'll use this formula for this guy. So, what was the thing? Dm omega square r. This is our r, by the way. And linear, right, so it's because it's linearly increasing r. What you can say is like dm is just equal to r upon the total length in this thing. So I don't know, call this thing L, right? Not the actual length of this rod, but something like that. L, right? R upon L, and that times the mass. Cool. So there we go. Just do the thing. dm is just this guy. Sorry, that's the no, that's kind of wrong. It should be dr upon L times m. So you got integration of dr upon L times m. L is, once again I repeat it, it's not this length. It's not, okay. It's this length. Okay, cool. So you got integration of dr upon m. That's the mass. You got omega square. Then r for this guy. That's this force. But then you actually want to take the, what do we call it? Oh, and okay, they give us angle theta, right? Cool. So given the theta, eventually figure that out. And also the length. Hey, if you already know the length, then it's not that bad actually. Where did the question go? Right, length L. Okay, let's not use all of that in that case. Let's do it the proper way. So you got this rod like this. We call this thing as x. This angle is theta. So this y component will just be x, x cosine, right, x cosine theta, and then this component will be x sine theta, right? Cool. Okay, this is a dm is just equal to dx upon L times m. Now it's perfectly correct. You don't have to actually take my word on it. Okay, so that's what dm is, right? What's d tau? uh right, this is going to be equal to what? What's the force? First of all, just dm omega squared r. So r is basically this guy, and that times, so about this point, right? So just gonna do this guy, sure, and everything you're doing is just like anti-clockwise as seen, like, okay. So this times y, so you can just do this thing. R is just that, it's just x sine theta, and then y is this x cosine theta, and there you go. That's your d tau. Not a vector, just think what is a scalar for now. Oh, come on, what's happening to it? Okay, now you know what d tau is, and just integrate this guy to get the actual tau. That's, I mean, I'm going correct, am I not? I am, of course. So m upon L omega squared sine theta cosine theta, right? All of that is out. You got x squared, and then this is just dx. All right. So integrate this thing from x is equal to negative L upon 2 to L upon 2, and that's gonna give us our tau, which is in, so omega is actually going in what direction? We don't know what that is. Oh, well, it doesn't matter. It's just outward, right? All the time. So it's right. It is. Wait, it's actually clockwise, not anti-clockwise. Right. Yes. Yeah, it's clockwise. Fine. Just solve this thing. Get over with it. So it is what? M omega squared sine theta cosine theta upon L. Then you got x cube upon 3, so just 3 over there, and then x cube, right? L upon 2 cube, L cube upon 8, plus, yeah, so like L cube upon 4. Cool. So this cancels L squared. ML squared omega squared sine cosine upon 12. That's the final thing. Wow, this was weird. I thought it was 0, but it's not. Okay, whatever. So when we actually start moving this thing, just by the centrifugal force itself, it will go clockwise. Which, okay, that makes perfect sense, because right, that's the way you would think, because yeah, you just want to straighten it up such that it can actually provide a tensile force that's in the x direction completely. Yeah, there you go. That's our torque. Oh, but in that case, like, oh, then there's also Coriolis force, isn't it? Because, right, there is a Coriolis force. Because this guy's R value is actually changing as this moves. That's not nice. Fine, whatever. So you got this as a thing. ML squared omega squared sine cosine upon 12. Next question, 270. Last question for this video. Okay. Conical pendulum, a thin uniform rod of length L and mass m, rotates uniformly about a vertical axis with angular velocity omega. The upper end of the rod is hinged. So you got this as a thing, right? And find the angle theta between the rod and the vertical. So this is the thing, okay. Angular velocity omega, right? So this is actually rotating in omega. Cool. Yeah, of course. So there we go. Find the angle theta between the rod and the vertical. This is not that hard, because hey, it's the same as this question actually, you know. Yeah, actually, that is the thing. It's really the same as this question. So in this rotating reference frame, just think about a centrifugal force that creates a torque, as we just saw, like in this case, it's like that. And right, so half of this rod is there, then you just got like ml squared omega squared sine cosine upon 24. But then the thing is the half the rod that also has mass, right, that guy's mass m is what we call m upon 2. So actually it's still this thing. It's just ml squared omega squared sine cosine upon 12. Right. So by symmetry you can say that, right? Because yeah, now you can definitely use symmetry. Previous case you couldn't use that. Now you can, because the torques are the same values. Sure. And those are scalars as well. So that makes sense. Okay. So you got this as our torque, and then you want what? You want what for what theta value does that happen, right? So cool. ml squared omega squared sine cosine upon 12. That torque is in clockwise direction for this guy. Yeah. Wait, that angle theta, it was different on. Oh, this is what we should call theta actually in that case. Because we want to be consistent. I know it's sine 2 theta and everything. It will actually make sense. Oh no, it's like 2 pi minus 2 theta. That would definitely make sense. So, it's, yeah, it would make a difference. So that's why you need here to be this thing. Okay, that's awesome. And what else? What other torque do we have? Gravity. So gravity is pushing in that direction. It is in the clockwise sense, and gravity is wait, what? It's in the clockwise sense, right? It's something. Oh no, it's not. Look, theta is more than pi, so more than pi upon 2. That's why this is actually going to be negative. So yeah, it's in the anti-clockwise sense. But in the clockwise sense, its value is this much. And this thing plus the gravity, or gravity torque actually. So it's mg throughout in this direction, right? So just torque about the center of mass and torque off on center of mass, right? Add them up. So our center of mass, oh god, this is not looking nice, unfortunately. What center of mass? The gravity. No, okay, the gravity will produce no torque. That's the reason you actually right. Of course. So about center of mass, no torque because of gravity. You can just always do this thing and 0. And then yeah, the clockwise torque of this guy, right? It's this distance. What is this distance actually? It's pi minus theta L upon 2 sine of L upon 2 sine theta, right? And what else? So you want the force, so mg. Yeah, that's the thing. So mg L sine theta. Yeah, that is the torque. That's equal to 0. Cool. So m cancels. Just get this as L cancels as well. So g sine theta. Oh, and in fact, sine theta also cancels because that's not 0. So omega square cosine upon 12. That's just equal to negative g. So c is just equal to negative g. Oh, wait, is that right or not? Oh, it's L over there as well. So of course, dimensional analysis. 12g upon omega square L. That's the thing. So what do you have? Theta is just pi minus cosine inverse of 12g upon omega square L. So that's the angle made with the vertical, the upward vertical. What do you want? You want acute angle or something? Upper end of the rod is hinged on. Find the angle theta between the rod and which vertical? It's the upward vertical or downward vertical? Both are vertical in the end. I think they mean like this vertical. So of course, in that case, this is this angle. So it's pi minus cosine inverse of all of this 12g upon omega square L. Yeah, that's right. Next question. Wait, okay, not next question. That's it. So this is it. I'll see you in the next video. Bye.